The Higgs boson or Higgs particle is an elementary particle initially theorized in 1964, whose discovery was announced at CERN on July 4, 2012. The discovery has been called monumental, because it appears to confirm the existence of the Higgs field, which is pivotal to the Standard Model and other theories within particle physics. It would explain why some fundamental particles have mass when the symmetries controlling their interactions should require them to be massless, and why the weak force has a much shorter range than the electromagnetic force. The discovery of the Higgs boson should allow physicists to finally validate the last untested area of the Standard Model's approach to fundamental particles and forces, guide other theories and discoveries in particle physics, and potentially lead to developments in new physics. This unanswered question in fundamental physics is of such importance that it led to a search of more than 40 years for the Higgs boson and finally the construction of one of the world's most expensive and complex experimental facilities to date, the Large Hadron Collider, able to create Higgs bosons and other particles for observation and study. On July 4, 2012, it was announced that a previously unknown particle with a mass between 125 and 127 a GeV-C2 had been detected. Physicists suspected at the time that it was the Higgs boson. By March 2013, the particle had been proven to behave, interact and decay in many of the ways predicted by the Standard Model, and was also tentatively confirmed to have positive parity and zero spin, two fundamental attributes of a Higgs boson. This appears to be the first elementary scalar particle discovered in nature. More data are needed to determine whether the particle discovered exactly matches the predictions of the Standard Model, or whether, as predicted by some theories, multiple Higgs bosons exist. The Higgs boson is named after Peter Higgs, one of 6 physicists who, in 1964, proposed the mechanism that suggested the existence of such a particle. Although Higgs's name has come to be associated with this theory, several researchers between about 1960 and 1972 each independently developed different parts of it. In mainstream media the Higgs boson has often been called the God particle, from a 1993 book on the topic. The nickname is strongly disliked by many physicists, including Higgs, who regard it as inappropriate sensationalism. In 2013 two of the original researchers, Peter Higgs and Francis-Xavier Englert, were awarded the Nobel Prize in Physics for their work and prediction. Englert's co-researcher Robert Brout had died in 2011 and the Nobel is not given posthumously except in unusual circumstances. In the Standard Model, the Higgs particle is a boson with no spin, electric charge, or color charge. It is also very unstable, decaying into other particles almost immediately. It is a quantum excitation of one of the 4 components of the Higgs field. The latter constitutes a scalar field, with 2 neutral and 2 electrically charged components, and forms a complex doublet of the weak isospin SU, symmetry. The field has a Mexican hat-shaped potential with non-zero strength everywhere, which in its vacuum state breaks the weak isospin symmetry of the electron-weak interaction. When this happens, 3 components of the Higgs field are absorbed by the SU, and U, gauge bosons to become the longitudinal components of the now massive W and Z bosons of the weak force. The remaining electrically neutral component separately couples to other particles known as fermions, causing these to acquire mass as well. Some versions of the theory predict more than one kind of Higgs fields and bosons. Alternative Higgsless models would have been considered if the Higgs boson were not discovered. A non-technical summary, Higgs terminology. Overview: in particle physics, elementary particles and forces give rise to the world around us. Nowadays, physicists explain the behavior of these particles and how they interact using the Standard Model, a widely accepted and remarkably accurate framework based on gauge invariants and symmetries, believed to explain almost everything in the world we see, other than gravity. But by around 1960 all attempts to create a gauge invariant theory for 2 of the 4 fundamental forces had consistently failed at one crucial point. Although gauge invariance seemed extremely important, it seemed to make any theory of electromagnetism and the weak force go haywire, by demanding that either many particles with mass were massless or that non-existent forces and massless particles had to exist. Scientists had no idea how to get past this point. Work done on superconductivity and broken symmetries around 1960 led physicist Philip Anderson to suggest in 1962 a new kind of solution that might hold the key. In 1964 a theory was created by 3 different groups of researchers that showed the problems could be resolved if an unusual kind of field existed throughout the universe. It would cause existing particles to acquire mass instead of new massless particles being formed. By 1972 it had been developed into a comprehensive theory and proved capable of giving sensible results. Although there was not yet any proof of such a field, calculations consistently gave answers and predictions that were confirmed by experiments, including very accurate predictions of several other particles, so scientists began to believe this might be true and to search for proof whether or not a Higgs field exists in nature. If this field did exist, this would be a monumental discovery for science and human knowledge, and is expected to open doorways to new knowledge in many fields. If not, then other more complicated theories would need to be explored. The easiest proof whether or not the field existed was by searching for a new kind of particle it would have to give off, known as Higgs bosons, or the Higgs particle. These would be extremely difficult to find, so it was only many years later that experimental technology became sophisticated enough to answer the question. While several symmetries in nature are spontaneously broken through a form of the Higgs mechanism, in the context of the Standard Model the term Higgs mechanism almost always means symmetry breaking of the electroweak field. It is considered proven, but the exact cause has been exceedingly difficult to prove. After 50 years, the Higgs boson's existence apparently proven in 2013 would finally confirm that the Standard Model is essentially correct and allow further development, while its non-existence would mean that other theories are needed instead. Various analogies have also been invented to describe the Higgs field and boson, including analogies with well-known symmetry-breaking effects such as the rainbow and prism, electric fields, ripples, and resistance of macro-objects moving through media, like people moving through crowds or some objects moving through syrup or molasses. However, analogies based on simple resistance to motion are inaccurate as the Higgs field does not work by resisting motion. Significance, scientific impact, evidence of the Higgs field and its properties would be extremely significant scientifically, for many reasons. The Higgs boson's importance is largely that it is able to be examined using existing knowledge and experimental technology, as a way to confirm and study the entire Higgs field theory. Conversely, proof that the Higgs field and boson do not exist would also be significant. In discussion form, the relevance includes real-world impact. As yet, there are no known immediate technological benefits of finding the Higgs particle. However, observers in both media and science point out that when fundamental discoveries are made about our world, their practical uses can take decades to emerge, but are often world-changing when they do. A common pattern for fundamental discoveries is for practical applications to follow later, once the discovery has been explored further, at which point they become the basis for social change and new technologies. For example, in the first half of the 20th century it was not expected that quantum mechanics would make possible transistors and microchips, mobile phones and computers, lasers and MRI scanners. Radio waves were described by their co-discoverer in 1888 as an interesting laboratory experiment with no useful purpose whatsoever, and are now used in innumerable ways. Positrons are used in hospital tomography scans, and special and general relativity, which explain black holes, also enable satellite-based GPS and satellite navigation. Electric power generation and transmission, motors, and lighting all stemmed from previous theoretical work on electricity and magnetism. Air conditioning and refrigeration resulted from thermodynamics. It is impossible to predict how seemingly esoteric knowledge may affect society in the future. Other observers highlight technological spin-offs from this and related particle physics activities, which have already brought major developments to society. For example, the World Wide Web as used today was created by physicists working in global collaborations on particle experiments at CERN to share their results, and the results of massive amounts of data produced by the Large Hadron Collider have already led to significant advances in distributed and cloud computing, now well established within mainstream services. History. Particle physicists study matter made from fundamental particles whose interactions are mediated by exchange particles, gauge bosons, acting as force carriers. At the beginning of the 1960s, a number of these particles had been discovered or proposed, along with theories suggesting how they relate to each other, some of which had already been reformulated as field theories in which the objects of study are not particles and forces, but quantum fields and their symmetries. However, attempts to unify known fundamental forces such as the electromagnetic force and the weak nuclear force were known to be incomplete. One known omission was that gauge-invariant approaches, including non-abelian models such as Younger-Mills theory, which held great promise for unified theories, also seemed to predict known massive particles as massless. Goldstone's theorem, relating to continuous symmetries within some theories, also appeared to rule out many obvious solutions, since it appeared to show that zero-mass particles would have to also exist that were simply not seen. According to Guralnick, physicists had no understanding how these problems could be overcome. Particle physicist and mathematician Peter Woit summarized the state of research at the time. Yang and Mills' work on non-abelian gauge theory had one huge problem. In perturbation theory it has massless particles which don't unregistered trademark T correspond to anything we see. One way of getting rid of this problem is now fairly well understood, the phenomenon of confinement realized in QCD, where the strong interactions get rid of the massless only states at long distances. By the very early 60s, people had begun to understand another source of massless particles, spontaneous symmetry breaking of a continuous symmetry. What Philip Anderson realized and worked out in the summer of 1962 was that, when you have both gauge symmetry and spontaneous symmetry breaking, the Nambu-Goldstone massless mode can combine with the massless gauge field modes to produce a physical massive vector field. This is what happens in superconductivity, a subject about which Anderson was one of the leading experts. Text condensed. The Higgs mechanism is a process by which vector bosons can get rest mass without explicitly breaking gauge invariance, as a byproduct of spontaneous symmetry breaking. The mathematical theory behind spontaneous symmetry breaking was initially conceived and published within Particle Physics by Yoichiro Nambu in 1960. The concept that such a mechanism could offer a possible solution for the mass problem was originally suggested in 1962 by Philip Anderson, and Abraham Klein and Benjamin Lee showed in March 1964 that Goldstone's theorem could be avoided this way in at least some non-relativistic cases and speculated it might be possible in truly relativistic cases. These approaches were quickly developed into a full relativistic model, independently and almost simultaneously, by three groups of physicists, by Francis-Noir Engelert and Robert Brout in August 1964, by Peter Higgs in October 1964, and by Gerald Guralnick, Carl Hagen, and Tom Kibble in November 1964. Higgs also wrote a short but important response published in September 1964 to an objection by Gilbert, which showed that if calculating within the radiation gauge, Goldstone's theorem and Gilbert's objection would become inapplicable. Properties of the model were further considered by Guralnick in 1965, by Higgs in 1966, by Kibble in 1967, and further by GHK in 1967. The original three 1964 papers showed that when a gauge theory is combined with an additional field that spontaneously breaks the symmetry, the gauge bosons can consistently acquire a finite mass. In 1967, Steven Weinberg and Abdus Salam independently showed how a Higgs mechanism could be used to break the electroweak symmetry of Sheldon-Glasgow's unified model for the weakened electromagnetic interactions, forming what became the standard model of particle physics. Weinberg was the first to observe that this would also provide mass terms for the Fermat's. However, the seminal papers on spontaneous breaking of gauge symmetries were at first largely ignored, because it was widely believed that the theories in question were a dead end, and in particular that they could not be renormalized. In 1971 a Euro 72, Martinus Veltman and Gerard T. Hooft proved renormalization of Younger Euromills was possible in two papers covering massless, and then massive, fields. Their contribution, and others' work on the renormalization group, including substantial theoretical work by Russian physicists, was eventually enormously profound and influential, but even with all key elements of the eventual theory published there was still almost no wider interest. For example, Coleman found in a study that essentially no one paid any attention to Weinberg's paper prior to 1971 now the most cited in particle physics and even in 1970 according to Politzer, Glasgow's teaching of the weak interaction contained no mention of Weinberg's, Salam's, or Glasgow's own work. In practice, Politzer states, almost everyone learned of the theory due to physicist Benjamin Lee, who combined the work of Veltman and T. Hooft with insights by others, and popularized the completed theory. In this way, from 1971, interest and acceptance exploded and the ideas were quickly absorbed in the mainstream. The resulting electroweak theory and Standard Model have correctly predicted weak neutral currents, 3 bosons, the top and charm quarks, and with great precision, the mass and other properties of some of these. Many of those involved eventually won Nobel Prizes or other renowned awards. A 1974 paper and comprehensive review in Reviews of Modern Physics commented that while no one doubted the mathematical correctness of these arguments, no one quite believed that nature was diabolically clever enough to take advantage of them, adding that the theory had so far produced meaningful answers that accorded with experiment, but it was unknown whether the theory was actually correct. By 1986 and again in the 1990s it became possible to write that understanding and proving the Higgs sector of the Standard Model was the central problem today in particle physics. A summary and impact of the PRL papers. The 3 papers written in 1964 were each recognized as milestone papers during Physical Review Literature's 50th anniversary celebration. Their 6 authors were also awarded the 2010 J.J. Sakurai Prize for Theoretical Particle Physics for this work. 2 of the 3 PRL papers contained equations for the hypothetical field that eventually would become known as the Higgs Field and its hypothetical quantum, the Higgs Boson. Higgs' subsequent 1966 paper showed the decay mechanism of the boson. Only a massive boson can decay and the decays can prove the mechanism. In the paper by Higgs the boson is massive, and in a closing sentence Higgs writes that an essential feature of the theory is the prediction of incomplete multiplets of scalar and vector bosons. In the paper by GHK the boson is massless and decoupled from the massive states. In reviews dated 2009 and 2011, Guralnick states that in the GHK model the boson is massless only in a lowest order approximation, but it is not subject to any constraint and acquires mass at higher orders, and adds that the GHK paper was the only one to show that there are no massless Goldstone bosons in the model and to give a complete analysis of the general Higgs mechanism. All 3 reached similar conclusions, despite their very different approaches. Higgs' paper essentially used classical techniques. Engelert and Brautz involved calculating vacuum polarization in perturbation theory around an assumed symmetry-breaking vacuum state, and GHK used operator formalism and conservation laws to explore in depth the ways in which Goldstone's theorem may be worked around. In addition to explaining how mass is acquired by vector bosons, the Higgs mechanism also predicts the ratio between the W boson and Z boson masses as well as their couplings with each other and with the Standard Model quarks and leptons. Subsequently, many of these predictions have been verified by precise measurements performed at the LEP and the SLC colliders, thus overwhelmingly confirming that some kind of Higgs mechanism does take place in nature, but the exact manner by which it happens has not yet been discovered. The results of searching for the Higgs boson are expected to provide evidence about how this is realized in nature. Theoretical properties. Theoretical need for the Higgs. Gauge invariance is an important property of modern particle theories such as the Standard Model, partly due to its success in other areas of fundamental physics such as electromagnetism and the strong interaction. However, there were great difficulties in developing gauge theories for the weak nuclear force or a possible unified electron-weak interaction. Fermions with a mass term would violate gauge symmetry and therefore cannot be gauge invariant. W and Z bosons are observed to have mass, but a boson mass term contains terms, which clearly depend on the choice of gauge, and therefore these masses too cannot be gauge invariant. Therefore it seems that none of the standard model fermions or bosons could begin with mass as an inbuilt property except by abandoning gauge invariance. If gauge invariance were to be retained, then these particles had to be acquiring their mass by some other mechanism or interaction. Additionally, whatever was giving these particles their mass, had to not break gauge invariance as the basis for other parts of the theories where it worked well, and had to not require or predict unexpected massless particles and long-range forces which did not actually seem to exist in nature. A solution to all of these overlapping problems come from the discovery of a previously unnoticed borderline case hidden in the mathematics of Goldstone's theorem, that under certain conditions it might theoretically be possible for a symmetry to be broken without disrupting gauge invariance and without any new massless particles or forces, and having sensible results mathematically. This became known as the Higgs mechanism. The Standard Model hypothesizes a field which is responsible for this effect, called the Higgs Field, which has the unusual property of a non-zero amplitude in its ground state. That is, a non-zero vacuum expectation value. It can have this effect because of its unusual Mexican hat-shaped potential whose lowest point is not at its center. Below a certain extremely high energy level, the existence of this non-zero vacuum expectation spontaneously breaks electroweak gauge symmetry, which in turn gives rise to the Higgs mechanism and triggers the acquisition of mass by those particles interacting with the field. This effect occurs because scalar field components of the Higgs field are absorbed by the massive bosons as degrees of freedom, and coupled to the fermions via Yukawa coupling, thereby producing the expected mass terms. In effect, when symmetry breaks under these conditions, the Goldstone bosons that arise interact with the Higgs field instead of becoming new massless particles. The intractable problems of both underlying theories neutralize each other, and the residual outcome is that elementary particles acquire a consistent mass based on how strongly they interact with the Higgs field. It is the simplest known process capable of giving mass to the gauge bosons while remaining compatible with gauge theories. Its quantum would be a scalar boson, known as the Higgs boson. Properties of the Standard Model. Higgs. In the Standard Model, the Higgs field consists of 4 components, 2 neutral ones and 2 charged component fields. Both of the charged components and one of the neutral fields are Goldstone bosons, which act as the longitudinal third polarization components of the massive W+, Euro, and Z bosons. The quantum of the remaining neutral component corresponds to the massive Higgs boson. Since the Higgs field is a scalar field, the Higgs boson has no spin. The Higgs boson is also its own antiparticle and is Cp even, and has 0 electric and color charge. The minimal Standard Model does not predict the mass of the Higgs boson. If that mass is between 115 and 180 GeV-C2, then the Standard Model can be valid at energy scales all the way up to the Planck scale. Many theorists expect new physics beyond the Standard Model to emerge at the TeV scale, based on unsatisfactory properties of the Standard Model. The highest possible mass scale allowed for the Higgs boson is 1.4 TeV. Beyond this point, the Standard Model becomes inconsistent without such a mechanism, because unitarity is violated in certain scattering processes. It is also possible, although experimentally difficult, to estimate the mass of the Higgs boson indirectly. In the Standard Model, the Higgs boson has a number of indirect effects. Most notably, Higgs loops result in tiny corrections to masses of W and Z bosons. Precision measurements of electroweak parameters, such as the Fermi constant and masses of Z bosons, can be used to calculate constraints on the mass of the Higgs. As of July 2011, the precision electroweak measurements tell us that the mass of the Higgs boson is likely to be less than about 161 GeV-C2 at 95% confidence level. These indirect constraints rely on the assumption that the Standard Model is correct. It may still be possible to discover a Higgs boson above these masses if it is accompanied by other particles beyond those predicted by the Standard Model. Production. If Higgs particle theories are correct, then a Higgs particle can be produced much like other particles that are studied, in a particle collider. This involves accelerating a large number of particles to extremely high energies and extremely close to the speed of light, then allowing them to smash together. Protons and lead ions are used at the LHC. In the extreme energies of these collisions, the desired esoteric particles will occasionally be produced, and this can be detected and studied. Any absence or difference from theoretical expectations can also be used to improve the theory. The relevant particle theory will determine the necessary kinds of collisions and detectors. The Standard Model predicts that Higgs bosons could be formed in a number of ways, although the probability of producing a Higgs boson in any collision is always expected to be very small. For example, only one Higgs boson per 10 billion collisions in the Large Hadron Collider. The most common expected processes for Higgs boson production are gluon fusion. If the collided particles are hadrons such as the proton or antiproton as is the case in the LHC and tevatron then it is most likely that two of the gluons binding the hadron together collide. The easiest way to produce a Higgs particle is if the two gluons combine to form a loop of virtual quarks. Since the coupling of particles to the Higgs boson is proportional to their mass, this process is more likely for heavy particles. In practice, it is enough to consider the contributions of virtual top and bottom quarks. This process is the dominant contribution at the LHC, and tevatron being about 10 times more likely than any of the other processes. Higgs Strahlung. If an elementary fermion collides with an antifermion for example, a quark with an antiquark or an electron with a positron the two can merge to form a virtual W or Z boson which, if it carries sufficient energy, can then emit a Higgs boson. This process was the dominant production mode at the LEP, where an electron and a positron collided to form a virtual Z boson, and it was the second largest contribution for Higgs production at the tevatron. At the LHC this process is only the third largest, because the LHC collides protons with protons, making a quark-antiquark collision less likely than at the tevatron. Higgs Strahlung is also known as associated production. Weak boson fusion. Another possibility when two fermions collide is that the two exchange a virtual W or Z boson, which emits a Higgs boson. The colliding fermions do not need to be the same type. So, for example, an up quark may exchange a Z boson with an anti-down quark. This process is the second most important for the production of Higgs particle at the LHC and LEP. Top fusion. The final process that is commonly considered is by far the least likely. This process involves two colliding gluons, which each decay into a heavy quark-antiquark pair. A quark and antiquark from each pair can then combine to form a Higgs particle. Decay. Quantum mechanics predicts that if it is possible for a particle to decay into a set of lighter particles, then it will eventually do so. This is also true for the Higgs boson. The likelihood with which this happens depends on a variety of factors including the difference in mass, the strength of the interactions, etc. Most of these factors are fixed by the Standard Model, except for the mass of the Higgs boson itself. For a Higgs boson with a mass of 126 GeV-C2 the SM predicts a mean lifetime of about 1.6 A, 10^22 AS. Since it interacts with all the massive elementary particles of the SM, the Higgs boson has many different processes through which it can decay. Each of these possible processes has its own probability, expressed as the branching ratio. The fraction of the total number decays that follows that process. The SM predicts these branching ratios as a function of the Higgs mass. One way that the Higgs can decay is by splitting into a fermion-antifermion pair. As general rule, the Higgs is more likely to decay into heavy fermions than light fermions, because the mass of a fermion is proportional to the strength of its interaction with the Higgs. By this logic the most common decay should be into a topo-anti-top quark pair. However, such a decay is only possible if the Higgs is heavier than 346 GeV-C2, twice the mass of the top quark. For a Higgs mass of 126 GeV-C2 the SM predicts that the most common decay is into a bottom-anti-bottom quark pair, which happens 56.1% of the time. The second most common fermion decay at that mass is a tau-anti-tau pair, which happens only about 6% of the time. Another possibility is for the Higgs to split into a pair of massive gauge bosons. The most likely possibility is for the Higgs to decay into a pair of W bosons, which happens about 23.1% of the time for a Higgs boson with a mass of 126 GeV-C2. The W bosons can subsequently decay either into a quark and an antiquark or into a charged lepton and a neutrino. However, the decays of W bosons into quarks are difficult to distinguish from the background, and the decays into leptons cannot be fully reconstructed. A cleaner signal is given by decay into a pair of Z bosons, if each of the bosons subsequently decays into a pair of easy-to-detect charged leptons. Decay into massless gauge bosons is also possible, but requires intermediate loop of virtual heavy quarks or massive gauge bosons. The most common such process is the decay into a pair of gluons through a loop of virtual heavy quarks. This process, which is the reverse of the gluon fusion process mentioned above, happens approximately 8.5% of the time for a Higgs boson with a mass of 126 GeV-C2. Much rarer is the decay into a pair of photons mediated by a loop of W bosons or heavy quarks, which happens only twice for every 1,000 decays. However, this process is very relevant for experimental searches for the Higgs boson, because the energy and momentum of the photons can be measured very precisely, giving an accurate reconstruction of the mass of the decaying particle. Alternative models. The minimal standard model as described above is the simplest known model for the Higgs mechanism with just one Higgs field. However, an extended Higgs sector with additional Higgs particle doublets or triplets is also possible, and many extensions of the standard model have this feature. The non-minimal Higgs sector favored by theory are the two Higgs doublet models, which predict the existence of a quintet of scalar particles, two CP even neutral Higgs bosons HO and HO, a CP odd neutral Higgs boson AO, and two charged Higgs particles Ha plus or minus. Supersymmetry also predicts relations between the Higgs boson masses and the masses of the gauge bosons, and could accommodate a 125 GeV-C2 neutral Higgs boson. The key method to distinguish between these different models involves study of the particles' interactions and exact decay processes, which can be measured and tested experimentally in particle collisions. In the type I2 HDM model, one Higgs doublet couples to up and down quarks, while the second doublet does not couple to quarks. This model has two interesting limits, in which the lightest Higgs couples to just fermions or just gauge bosons, but not both. In the type I2 HDM model, one Higgs doublet only couples to up-type quarks, the other only couples to down-type quarks. The heavily researched minimal supersymmetric standard model includes a type I2 HDM Higgs sector, so it could be disproven by evidence of a type I2 HDM Higgs. In other models, the Higgs scalar is a composite particle. For example, in Technicolor the role of the Higgs field is played by strongly bound pairs of fermions called techniquarks. Other models feature pairs of top quarks. In yet other models, there is no Higgs field at all and the electroweak symmetry is broken using extra dimensions. Further theoretical issues and hierarchy problem. The standard model leaves the mass of the Higgs boson as a parameter to be measured, rather than a value to be calculated. This is seen as theoretically unsatisfactory, particularly as quantum corrections should apparently cause the Higgs particle to have a mass immensely higher than that observed, but at the same time the standard model requires a mass of the order of 100 to 1000 GeV to ensure unitarity. Reconciling these points appears to require explaining why there is an almost perfect cancellation resulting in the visible mass of 125 GeV, and it is not clear how to do this. Because the weak force is about 1032 times stronger than gravity, and the Higgs boson's mass is so much less than the Planck mass or the grand unification energy, it appears that either there is some underlying connection or reason for these observations which is unknown and not described by the standard model, or some unexplained and extremely precise fine-tuning of parameters however at present neither of these explanations is proven. This is known as a hierarchy problem. More broadly, the hierarchy problem amounts to the worry that a future theory of fundamental particles and interactions should not have excessive fine-tunings or unduly delicate cancellations, and should allow masses of particles such as the Higgs boson to be calculable. The problem is in some ways unique to spin-O particles, which can give rise to issues related to quantum corrections that do not affect particles with spin. A number of solutions have been proposed, including supersymmetry, conformal solutions and solutions via extra dimensions such as brane-world models. Experimental search. To produce Higgs bosons, two beams of particles are accelerated to very high energies and allowed to collide within a particle detector. Occasionally, although rarely, a Higgs boson will be created fleetingly as part of the collision byproducts. Because the Higgs boson decays very quickly, particle detectors cannot detect it directly. Instead, the detectors register all the decay products, and from the data the decay process is reconstructed. If the observed decay products match a possible decay process of a Higgs boson, this indicates that a Higgs boson may have been created. In practice, many processes may produce similar decay signatures. Fortunately, the Standard Model precisely predicts the likelihood of each of these, and each known process, occurring. So, if the detector detects more decay signatures consistently matching a Higgs boson than would otherwise be expected if Higgs bosons did not exist, then this would be strong evidence that the Higgs boson exists. Because Higgs boson production in a particle collision is likely to be very rare, and many other possible collision events can have similar decay signatures, the data of hundreds of trillions of collisions needs to be analyzed and must show the same picture before a conclusion about the existence of the Higgs boson can be reached. To conclude that a new particle has been found, particle physicists require that the statistical analysis of two independent particle detectors each indicate that there is lesser than a 1 in a million chance that the observed decay signatures are due to just background random standard model events, that is, that the observed number of events is more than 5 standard deviations different from that expected if there was no new particle. More collision data allows better confirmation of the physical properties of any new particle observed, and allows physicists to decide whether it is indeed a Higgs boson as described by the Standard Model or some other hypothetical new particle. To find the Higgs boson, a powerful particle accelerator was needed, because Higgs bosons might not be seen in lower energy experiments. The collider needed to have a high luminosity in order to ensure enough collisions were seen for conclusions to be drawn. Finally, advanced computing facilities were needed to process the vast amount of data produced by the collisions. For the announcement of July 4, 2012, a new collider known as the Large Hadron Collider was constructed at CERN with a planned eventual collision energy of 14 TeV over 7 times any previous collider and over 300 trillion LHC proton collisions were analyzed by the LHC computing grid, the world's largest computing grid, comprising over 170 computing facilities in a worldwide network across 36 countries. Search prior to July 4, 2012, the first extensive search for the Higgs boson was conducted at the Large Electron-Positron Collider at CERN in the 1990s. At the end of his service in 2000, LEP had found no conclusive evidence for the Higgs. This implied that if the Higgs boson were to exist it would have to be heavier than 114.4 GeV-C2. The search continued at Fermilab in the United States, where the Tevatron the collider that discovered the top quark in 1995 had been upgraded for this purpose. There was no guarantee that the Tevatron would be able to find the Higgs, but it was the only supercollider that was operational since the Large Hadron Collider was still under construction and the planned superconducting supercollider had been cancelled in 1993 and never completed. The Tevatron was only able to exclude further ranges for the Higgs mass, and was shut down on September 30, 2011 because it no longer could keep up with the LHC. The final analysis of the data excluded the possibility of a Higgs boson with a mass between 147 GeV-C2 and 180 GeV-C2. In addition, there was a small excess of events possibly indicating a Higgs boson with a mass between 115 GeV-C2 and 140 GeV-C2. The Large Hadron Collider at CERN in Switzerland was designed specifically to be able to either confirm or exclude the existence of the Higgs boson. Built in a 27 km tunnel under the ground near Geneva, originally inhabited by LEP, it was designed to collide two beams of protons, initially at energies of 3.5 TeV per beam, or almost 3.6 times that of the tevatron, and upgradable to 2.7 TeV in future. Theories suggested if the Higgs boson existed, collisions at these energy levels should be able to reveal it. As one of the most complicated scientific instruments ever built, its operational readiness was delayed for 14 months by a magnet quench event 9 days after its inaugural tests, caused by a faulty electrical connection that damaged over 50 superconducting magnets and contaminated the vacuum system. Data collection at the LHC finally commenced in March 2010. By December 2011, the two main particle detectors at the LHC, ATLAS and CMS, had narrowed down the mass range where the Higgs could exist to around 116 to 130 GeV and 115 to 127 GeV. There had also already been a number of promising event excesses that had evaporated, and proven to be nothing but random fluctuations. However, from around May 2011, both experiments had seen among their results, the slow emergence of a small yet consistent excess of gamma and 4-lepton decay signatures and several other particle decays, all hinting at a new particle at a mass around 125 GeV. By around November 2011, the anomalous data at 125 GeV was becoming too large to ignore, and the team leaders at both ATLAS and CMS each privately suspected they might have found the Higgs. On November 28, 2011, at an internal meeting of the two team leaders and the Director General of CERN, the latest analyses were discussed outside their teams for the first time, suggesting both ATLAS and CMS might be converging on a possible shared result at 125 GeV, and initial preparations commenced in case of a successful finding. While this information was not known publicly at the time, the narrowing of the possible Higgs range to around 115–130 GeV and the repeated observation of small but consistent event excesses across multiple channels at both ATLAS and CMS in the 124 to 126 GeV region were public knowledge with a lot of interest. It was therefore widely anticipated around the end of 2011, that the LHC would provide sufficient data to either exclude or confirm the finding of a Higgs boson by the end of 2012, when their 2012 collision data had been examined. Discovery of candidate boson at CERN. On June 22, 2012, CERN announced an upcoming seminar covering tentative findings for 2012, and shortly afterwards rumors began to spread in the media that this would include a major announcement, but it was unclear whether this would be a stronger signal or a formal discovery. Speculation escalated to a fever pitch when reports emerged that Peter Higgs, who proposed the particle, was to be attending the seminar, and that 5 leading physicists had been invited, generally believed to signify the 5 living 1964 authors, with Higgs, Engelert, Goralnik, Hagen attending and Kibble confirming his invitation. On July 4, 2012, both of the CERN experiments announced they had independently made the same discovery, CMS of a previously unknown boson with mass 125.3 a plus or minus 0.6 GeV-C2 and ATLAS of a boson with mass 126.5 GeV-C2. Using the combined analysis of two interaction types, both experiments reached a local significance of 5 sigma, or less than a 1 in 1 million chance of error. When additional channels were taken into account, the CMS significance was reduced to 4.9 sigma. The two teams had been working blinded from each other from around late 2011 or early 2012, meaning they did not discuss their results with each other, providing additional certainty that any common finding was genuine validation of a particle. This level of evidence, confirmed independently by two separate teams and experiments, meets the formal level of proof required to announce a confirmed discovery. On July 31, 2012, the ATLAS collaboration presented additional data analysis on the observation of a new particle, including data from a third channel, which improved the significance to 5.9 sigma and mass 126.0 plus or minus 0.4 plus or minus 0.4 GeV-C2, and CMS improved the significance to 5 sigma and mass 125.3 a plus or minus 0.4 a plus or minus 0.5 GeV-C2. The new particle tested as a possible Higgs boson. Following the 2012 discovery, it was still unconfirmed whether or not the 125 GeV-C2 particle was a Higgs boson. On one hand, observations remain consistent with the observed particle being the standard model Higgs boson, and the particle decayed into at least some of the predicted channels. Moreover, the production rates and branching ratios for the observed channels broadly matched the predictions by the standard model within the experimental uncertainties. However, the experimental uncertainties currently still left room for alternative explanations, meaning an announcement of the discovery of a Higgs boson would have been premature. To allow more opportunity for data collection, the LHC's proposed 2012 shutdown and 2013 Euro 14 upgrade were postponed by 7 weeks into 2013. In November 2012, in a conference in Kyoto, researchers said evidence gathered since July was falling into line with the basic standard model more than its alternatives, with a range of results for several interactions matching that theory's predictions. Physicist Matt Strassler highlighted considerable evidence that the new particle is not a pseudoscalar negative parity particle, evaporation, or lack of increased significance for previous hints of non-standard model findings, expected standard model interactions with W and Z bosons, absence of significant new implications for or against supersymmetry, and in general no significant deviations to date from the results expected of a standard model Higgs boson. However, some kinds of extensions to the standard model would also show very similar results. So commentators noted that based on other particles that are still being understood long after their discovery, it may take years to be sure, and decades to fully understand the particle that has been found. These findings meant that as of January 2013, scientists were very sure they had found an unknown particle of mass 125 a GeV-C2, and had not been misled by experimental error or a chance result. They were also sure, from initial observations, that the new particle was some kind of boson. The behaviors and properties of the particle, so far as examined since July 2012, also seemed quite close to the behaviors expected of a Higgs boson. Even so, it could still have been a Higgs boson or some other unknown boson, since future tests could show behaviors that do not match a Higgs boson. So as of December 2012, CERN still only stated that the new particle was consistent with the Higgs boson, and scientists did not yet positively say it was the Higgs boson. Despite this, in late 2012, widespread media reports announced that a Higgs boson had been confirmed during the year. In January 2013, CERN Director General Rolf Dieter stated that based on data analysis to date, an answer could be possible towards mid-2013, and the Deputy Chair of Physics at Brookhaven National Laboratory stated in February 2013 that a definitive answer might require another few years after the collider's 2015 restart. In early March 2013, CERN Research Director Sergio Bertolucci stated that confirming spin-error was the major remaining requirement to determine whether the particle is at least some kind of Higgs boson. Confirmation of new particle as a Higgs boson, and current status. On March 14, 2013, CERN confirmed that CMS and ATLAS have compared a number of options for the spin parity of this particle, and these all prefer no spin and positive parity, two fundamental criteria of a Higgs boson consistent with the standard model. This, coupled with the measured interactions of the new particle with other particles, strongly indicates that it is a Higgs boson. This also makes the particle the first elementary scalar particle to be discovered in nature. Examples of tests used to validate whether the 125 GeV particle is a Higgs boson. Public discussion, naming, names used by physicists. The name most strongly associated with the particle and field is the Higgs boson and Higgs field. For some time the particle was known by a combination of its PRL author names, for example the Brauter-Engelerter-Higgs particle, the Anderson-Higgs particle, or the Engelerter-Brauter-Higgs-Goralnica-Hagina-Kibble mechanism, and these are still used at times. fueled in part by the issue of recognition and a potential shared Nobel Prize. The most appropriate name is still occasionally a topic of debate as at 2012. A considerable amount has been written on how Higgs' name came to be exclusively used. Two main explanations are offered. Nickname: the Higgs boson is often referred to as the God particle in popular media outside the scientific community. The nickname comes from the title of a 1993 book on the Higgs boson and particle physics by Nobel Physics Prize winner and Fermilab director Leon Lederman. Lederman wrote it in the context of failing U.S. government support for the superconducting supercollider, a part-constructed Titanic competitor to the Large Hadron Collider with planned collision energies of 2.20 TeV that was championed by Lederman since its 1983 inception and shut down in 1993. The book sought in part to promote awareness of the significance and need for such a project in the face of its possible loss of funding. While media use of this term may have contributed to wider awareness and interest, many scientists feel the name is inappropriate since it is sensational hyperbole and misleads readers. The particle also has nothing to do with God, leaves open numerous questions in fundamental physics, and does not explain the ultimate origin of the universe. Higgs, an atheist, was reported to be displeased and stated in a 2008 interview that he found it embarrassing, because it was the kind of misuse which I think might offend some people. Science writer Ian Sample stated in his 2010 book On the Search that the nickname is universally hated by physicists and perhaps the worst derided in the history of physics, but that the publisher rejected all titles mentioning Higgs as unimaginative and too unknown. Lederman begins with a review of the long human search for knowledge, and explains that his tongue-in-cheek title draws an analogy between the impact of the Higgs field on the fundamental symmetries at the Big Bang, and the apparent chaos of structures, particles, forces and interactions that resulted and shaped our present universe, with the biblical story of Babel in which the primordial single language of early Genesis was fragmented into many disparate languages and cultures. Today, we have the Standard Model, which reduces all of reality to a dozen or so particles and 4 forces. It's a hard-won simplicity. And remarkably accurate. But it is also incomplete and, in fact, internally inconsistent. This boson is so central to the state of physics today, so crucial to our final understanding of the structure of matter, yet so elusive, that I have given it a nickname, the God particle. Why God particle? 2 reasons. 1, the publisher wouldn't let us call it the goddamn particle, though that might be a more appropriate title, given its villainous nature and the expense it is causing. And 2, there is a connection, of sorts, to another book, a much older one. Lederman whimsically asks whether the Higgs boson was added just to perplex and confound those seeking knowledge of the universe, and whether physicists will be confounded by it as recounted in that story, or ultimately surmount the challenge and understand, how beautiful is the universe, God has made. Other proposals, a renaming competition by British newspaper The Guardian in 2009 resulted in their science correspondent choosing the name the champagne bottle boson as the best submission. The bottom of a champagne bottle is in the shape of the Higgs potential and is often used as an illustration in physics lectures. So it's not an embarrassingly grandiose name, it is memorable, and it has some physics connection too. The name Higgson was suggested as well, in an opinion piece in the Institute of Physics online publication physicsworld.com. Media explanations and analogies. There has been considerable public discussion of analogies and explanations for the Higgs particle and how the field creates mass, including coverage of explanatory attempts in their own right and a competition in 1993 for the best popular explanation by then UK Minister for Science Sir William Waldegrave and articles in newspapers worldwide. An educational collaboration involving an LHC physicist and a high school teachers at CERN educator suggests that dispersion of light responsible for the rainbow and dispersive prism is a useful analogy for the Higgs field symmetry breaking and mass causing effect. Matt Strassler uses electric fields as an analogy. Some particles interact with the Higgs field while others don't. Unregistered trademark T. Those particles that feel the Higgs field act as if they have mass. Something similar happens in an electric field. Charged objects are pulled around and neutral objects can sail through unaffected. So you can think of the Higgs search as an attempt to make waves in the Higgs field, create Higgs bosons to prove unregistered trademark is really there. A similar explanation was offered by The Guardian. The Higgs boson is essentially a ripple in a field said to have emerged at the birth of the universe and to span the cosmos to this day. The particle is crucial, however, it is the smoking gun, the evidence required to show the theory is right. The Higgs field's effect on particles was famously described by physicist David Miller as akin to a room full of political party workers spread evenly throughout a room. The crowd gravitates to and slows down famous people but does not slow down others. He also drew attention to well-known effects in solid-state physics where an electron's effective mass can be much greater than usual in the presence of a crystal lattice. Analogies based on drag effects, including analogies of syrup or molasses, are also well known, but can be somewhat misleading since they may be understood as saying that the Higgs field simply resists some particles' motion but not others. A simple resistive effect could also conflict with Newton's third law. Recognition and awards. There has been considerable discussion of how to allocate the credit if the Higgs boson is proven, made more pointed as a Nobel Prize had been expected, and the very wide basis of people entitled to consideration. These include a range of theoreticians who made the Higgs mechanism theory possible, the theoreticians of the 1964 PRL papers, the theoreticians who derived from these, a working electroweak theory and the Standard Model itself, and also the experimentalists at CERN and other institutions who made possible the proof of the Higgs field and boson in reality. The Nobel Prize is a limit of 3 persons to share an award, and some possible winners are already prize holders for other work, or are deceased. Existing prizes for works relating to the Higgs field, boson, or mechanism include, Nobel Prize in Physics Weinberg and Salam, for contributions to the theory of the unified weak and electromagnetic interaction between elementary particles, Nobel Prize in Physics T. Hooft and Veltman, for elucidating the quantum structure of electroweak interactions in physics, Nobel Prize in Physics Nambu, for the discovery of the mechanism of spontaneous broken symmetry in subatomic physics, J. Sakurai Prize for Theoretical Particle Physics Hagen, Engelert, Goralnik, Higgs, Brout, and Kibble, for elucidation of the properties of spontaneous symmetry breaking in 4-dimensional relativistic gauge theory and of the mechanism for the consistent generation of vector boson masses, Wolf Prize Engelert, Brout, and Higgs, Nobel Prize in Physics, Peter Higgs and Francis Engelert, for the theoretical discovery of a mechanism that contributes to our understanding of the origin of massive subatomic particles, and which recently was confirmed through the discovery of the predicted fundamental particle, by the ATLAS and CMS experiments at CERN's Large Hadron Collider. Additionally, Physical Review Letters 50-year review recognized the 1964 PRL papers and Weinberg's 1967 paper A Model of Leptons milestone letters. Following reported observation of the Higgs-like particle in July 2012. Several Indian media outlets reported on the supposed neglect of credit to Indian physicist Satyendranath Bose, after whose work in the 1920s the class of particles bosons is named. Technical aspects and mathematical formulation. In the Standard Model, the Higgs field is a 4-component scalar field that forms a complex doublet of the weak isospin SU, symmetry. While the field has charge plus 1/2 under the weak hypercharge U, symmetry. The Higgs part of the Lagrangian is where under the gauge bosons of the SU, and U, symmetries, and their respective coupling constants, a complete set generators of the SU, symmetry, and, so that the ground state breaks the SU, symmetry. The ground state of the Higgs field is degenerate with different ground states related to each other by a SU, gauge transformation. It is always possible to pick a gauge such that in the ground state, the expectation value of in the ground state is then, where the measured value of this parameter is 246 a GeVC2. It has units of mass, and is the only free parameter of the Standard Model that is not a dimensionless number. Quadratic terms in and arise, which give masses to the W and Z bosons, with their ratio determining the Weinberg angle, and leave a massless U(1) photon. The quarks and the leptons interact with the Higgs field through Yukawa interaction terms. Where are left-handed and right-handed quarks and leptons of the ith generation, are matrices of Yukawa couplings where Hc denotes the Hermitian conjugate terms. In the symmetry-breaking ground state, only the terms containing remain, giving rise to mass terms for the fermions. Rotating the quark and lepton fields to the basis where the matrices of Yukawa couplings are diagonal, one gets where the masses of the fermions are, and denote the eigenvalues of the Yukawa matrices. See also, Standard Model, Quantum Gauge Theory, Introduction to Quantum Mechanics, Non-commutative Standard Model and Non-commutative Geometry generally, Standard Model, Other, Bussy-Einstein Statistics, Delitzsch plot, Higgs boson in fiction, Quantum triviality, ZZ-Der boson, Scalar boson, Stueck-Elberg action, notes. References. Further reading. External links, Popular Science, Mass Media, and General Coverage, Hunting the Higgs boson at CMS Experiment, at CERN, the Higgs boson by the CERN Exploratorium. Particle Fever, documentary film about the search for the Higgs boson. The Atom Smashers, documentary film about the search for the Higgs boson at Fermilab. Collected articles at The Guardian, video CERN announcement on July 4, 2012, of the discovery of a particle which is suspected will be a Higgs boson. Video 1 plus Video 2 a Higgs boson explained by CERN physicist, Dr. Daniel Whiteson. How Stuff Works, What Exactly is the Higgs boson? Carroll, Sean. Higgs boson with Sean Carroll. 60 Symbols. University of Nottingham Overby, Dennis. Chasing the Higgs boson, How Two Teams of Rivals at CERN Searched for Physics' Most Elusive Particle. New York Times Science Pages. Retrieved July 22, 2013. A New York Times behind-the-scenes style article on the Higgs search at Atlas and CMS, the story of the Higgs theory by the authors of the PRL papers and others closely associated. Higgs, Peter. My Life as a Boson. Talk given at King's College, London, November 24, 2010. Retrieved January 17, 2013. Kibble, Tom. Engelerte Brauter Higgs Goraunica Hagina Kibble mechanism. Scholarpedia. Retrieved January 17, 2013. Goraunik, Gerald. The History of a Goraunik, Hargon and Kibble Development of the Theory of Spontaneous Symmetry Breaking and Gauge Particles. International Journal of Modern Physics A24, 2601 2627. AR-Ziv, 0907.3466. Bibcode, 2009 IJMPA 24.26001 GDOI, 10.1142 per second 021751X090454331. Goraunik, Gerald. The Beginnings of Spontaneous Symmetry Breaking in Particle Physics. Proceedings of the DPF 2011 Conference, Providence, Rhode Island, 8 August 13, 2011. AR-Ziv, 1110.2253 Physics Hist Ph, and Goraunik, Gerald. Heretical Ideas that Provided the Cornerstone for the Standard Model of Particle Physics. SPG Mittelungen March 2013, number 39. And talk at Brown University about the 1964 PRL papers, Philip Anderson on symmetry breaking and superconductivity and its migration into particle physics, and the PRL papers. Cartoon about the search, Cham, Jorge. True Tales from the Road, the Higgs boson re-explained. Piled higher and deeper. Retrieved February 25, 2014. Significant Papers and Other, Observation of a New Particle in the Search for the Standard Model Higgs Boson with the Atlas Detector at the LHC, Observation of a New Boson at a Mass of 125 GeV with the CMS Experiment at the LHC, Particle Data Group, Review of Searches for Higgs Bosons. 2001, A Space-Time Odyssey. Proceedings of the inaugural conference of the Michigan Center for Theoretical Physics in Michigan, USA, 21 May 25, 2001 ed. Michael J. Duff, James T. Liu, ISBN 978-981-238-231-3, containing Higgs' story of the Higgs boson. A. Migdal and A. M. Polyakov, Spontaneous Breakdown of Strong Interaction Symmetry in the Absence of Massless Particles, SOV JJETP 24, 91, example of a 1966 Russian paper on the subject. Introductions to the Field, Spontaneous Symmetry Breaking, Gauge Theories, the Higgs Mechanism and All That, an introduction of 47 pages covering the development, history and mathematics of Higgs theories from around 1950 to 1974.